So let's move on to the next type of function we're going to need to differentiate, which are trigonometric functions. So starting with the simplest, which are sine and cosine, here are the derivatives. So the derivative of sine is cosine, and the derivative of cosine is minus sine. So be careful with the signs, right? The derivative of sine is cosine, derivative of cosine is minus sine. And just one comment about trig functions using with calculus is that always we're going to use radians. So we're going to be doing, for instance, sine of pi over 6, sine of pi over 2, not sine of 90 or anything like that. So in calculus trig functions, we always use radians. And we should know the values of trig functions at angles that are multiples of pi over 6 and pi over 4. For instance, when you're doing calculations in calculus, you might be asked to substitute some angles, or you might need to sub in some angles and evaluate. You'll need to know the values of the trig functions at these. And there are a couple of tricks for doing that. So if you know the values of sine and cosine at the right angles, then you can work out tangent and secant and cosecant and all the others from knowing sine and cosine, just because we can write the other trig functions in terms of sine and cosine. And if you know the values of sine and cosine, say in the top right quadrant, then you can work out the values in the other quadrants by using symmetries. So I don't want to go into that too much here, but know that there are rules for doing that. And if not, if you don't know them right now, you should go away and look them up and figure it out, because they will keep coming back. So make sure you know those. Okay, so for instance, we can combine the derivative of sine and cosine with things we already talked about in the last section with product and quotient rules. So for instance, here we have a product exponential function times a trig function. So the derivative of 2 to the x sine x, we should fix the first function and differentiate the second. So we get 2 to the x cosine x. And then we should do it the other way. So fix the second function sine x, differentiate the first, we get 2 to the x ln 2 times sine x. So nothing too strange. Okay, and since we know how to write the other trig functions in terms of sine and cosine, we can use the derivatives of sine and cosine to differentiate the other functions. So here, for instance, I'm claiming the derivative of tangent is secant squared. Why? Well, we can write tangent as sine x divided by cosine x. And now this is a quotient of two functions that we know how to differentiate, so we can apply the quotient rule. Right, and the quotient rule says the derivative of a quotient is the bottom times the derivative of the top, minus the top times the derivative of the bottom, all divided by the bottom squared. And then if we actually go through with that, we get cosine times the derivative of sine, so we get cosine squared. And then we get minus sine times the derivative of cosine. Derivative of cosine is minus sine, so we get plus sine squared. And then we notice on the top we have sine squared plus cosine squared, which is 1. So we have 1 over cosine squared, which is another name for secant squared. So the derivative of tangent is secant squared, just because we can write tangent in terms of sine and cosine and use the other rules we know. So you could do this for all the trig functions. So here's a summary. Derivative of sine and cosine and tangent we talked about. The derivative of cot is minus cosecant squared. The derivative of secant is secant x times tangent x. Derivative of cosecant x is minus cosecant x times cot x. So how would you do these? For instance, secant you can write as 1 over cosine. So you can use the quotient rule. Cotangent is cosine divided by sine. Use the quotient rule. Cosecant is 1 divided by sine. And notice that the formulas for derivatives of tangent and cotangent look kind of similar, except secant is swapped to cosecant and then minus sign is added. And similarly, it's the derivative of secant and cosecant are kind of similar, except we swap to the evil twin. Secant is swapped to cosecant, tangent is swapped to cotangent, and then we have to add a minus sign. So these are worth knowing. Yeah, definitely I recommend knowing all of these. Okay, so let's talk a little bit about how that comes about. So for instance, why is the derivative of sine cosine? Or at least let's examine that a little. So suppose we were to try to work out the derivative using the definition. So f of x is sine x. What do we have to do? F of x plus h minus f of x divided by h, take the limit. So here we get sine of x plus h minus sine x divided by h. And then on the next line, I use the sine addition formula to expand this. So remember, sine of a plus b is sine a times cosine b plus cosine a times sine b. So we expanded. And then I group the terms. So everything there was a sine x, they go together. So we get sine x times cosine h minus 1. And then we get cosine x times sine h. And then let's split it apart. So remember the limit of a sum, I'm assuming for the moment that the individual limits exist. So then the limit of a sum is the sum of the limits, and we can bring out things that don't depend on h out of the limit. So we're going to get sine x times the limit of cosine h minus 1 over h, cosine x times the limit of sine h over h. And these limits are not easy limits. So if you try to naively plug in, for instance, you would get, cosine of 0 minus 1 is going to be 1 minus 1 is going to be 0. On the bottom, you're going to get 0. And then similarly here on the top and the bottom, you get 0. So these are not easy limits. You need to, we're not going to go into why it's true, but there are, you can find proofs that rely on geometric reasoning or other tools. But what should they be? So we're aiming to have cosine x as our derivative. We said the derivative of sine should be cosine. So out here we should get sine. Sorry, we should get cosine. So if we're going to get cosine in the end, then the bit that's next to sine should be 0. So this limit should be 0. And then if we're going to get cosine in the end, then the piece that's next to cosine should be 1. So this limit has to be 1. And in fact, that's true. So these are going to be useful limits that we need to be aware of. So the limit of sine h divided by h is 1, and the limit of cosine h minus 1 divided by h equals 0. Sometimes people ask me, maybe you've seen a little bit of calculus before and you've seen L'Hopital's rule. And they say, these limits, I could maybe evaluate them using L'Hopital's rule, which says that, if we have a limit and the top is going to 0, the bottom is going to 0, then I can work out the limit using the derivative of the top divided by derivative of the bottom and taking the limit of that instead. But you can't do that because here we are already using these limits in order to work out the derivative of sine, right? I'm using these limits to differentiate sine. So I cannot then, use the fact that the derivative of sine is cosine to apply L'Hopital's rule, because I cannot use derivatives in order to prove these limits because I'm using these limits to prove the derivative, if that makes sense. So that would be circular reasoning. So L'Hopital's rule will not be acceptable to do that. Okay, so I mean, if I want to prove that A implies something, then I cannot use my conclusion to prove what I want, right? I have to do something else. Okay, anyway, moving away from that, so let's use these limits to evaluate new limits. And the idea is we're going to be able to use them to find limits that are kind of similar, especially the first one, so the limit of sine h divided by h equals 1. So sometimes it doesn't really matter what the h is, so h might look like something different. All it matters is that I have the limit of sine something divided by something, where the something is going to 0. So the something might look a little different, but whatever my thing is, they match in the numerator and the denominator, and they're going to 0. So for instance here, let's try to look at the limit of sine 8x divided by 3x. And it doesn't look like sine of something divided by something, right? Because the 8x and the 3x are different. So I want to do some kind of trick to make them, to have the same thing in the numerator and the denominator, inside the sine and on the denominator. And I can't do anything with the 8x. The 8x is stuck inside the sine, right? Sine of 8x is definitely not equal to 8 sine x. I cannot bring the 8 out in front. That would be wrong. So I can't do that. The best I can do is manipulate the 3x, which is on the bottom. So that's not being applied to any function. I'm pretty free to, multiply the top and bottom by things and divide the top and bottom by things to play around with this. So what's the right way to write it? Okay, I cannot do anything with the sine 8x, as we said. What do I want? I really want to have 8x on the bottom because I know that if I have sine of something divided by something, right? If I have sine h over h, if I have sine of anything divided by the same thing, then I can say something about the limit. So my dream is to have sine 8x divided by 8x, but I actually had sine 8x divided by 3x. So if I want to keep them equal, then I have to multiply by 8 over 3, right? So that the 8s will cancel and I'm left with 3 on the bottom. So as usual, the questions are they equal? And why did I do that? Well, they are equal. If you cancel the 8s, you have the 3 on the bottom. Why did I do that? Well, now I can take the limit, right? I have x is going to 0, so 8x is going to 0. So I have sine of something divided by something where my thing is going to 0, so I get 1. And then I'm just left with 8 over 3. So here the answer is 8 over 3. Okay, but notice this was definitely not, I did not bring the 8 out of the sine. That would not make sense. Okay, so I had to manipulate the bottom. Okay, another simple example, for instance, to find the limit of x times cotangent of x. For instance, I can't just plug in with any of these, right? If I try to do that, x would be going to 0. Cotangent is cosine divided by sine. That would be going to plus or minus infinity. So I can't just plug in. I have to do something. So let's write out what is x cotangent x in terms of cosine and sine. So I get cotangent is cosine divided by sine. So I would get x times cosine divided by sine. And then I want to write it in terms of the limits that I already know from the previous slide, which was sine x divided by x or cosine x minus 1 divided by x. So I want to use the first one. So instead of writing it as x cosine x divided by sine x, I can write it as cosine x divided by sine x over x. And now, so they are really equal. If I multiply, say I divide top and bottom of the middle by x, then I will get cosine x divided by sine x over x. So they are equal. And now I can take the limit of the top and bottom separately, right? So I know that sine x over x goes to 1 as x goes to 0. I know that cosine is continuous, so I can take a limit that goes to cosine of 0, which is 1, as x goes to 0. Okay, so the top and bottom are both going to 1. In the end, we get 1. So the limit is going to be 1. So we can use the two limits we talked about to find other limits by doing algebra to write other expressions in terms of things we already understand. Okay, so we talked about derivatives of sine and cosine, and then using them, we got the derivatives of tangent, cotangent, secant, cosecant, all the other trig functions. And then we saw how do they come about? They come about from knowing the limit of sine x over x and the limit of cosine x minus 1 divided by x. And then we saw how to apply those to find other limits using algebra. Okay, thanks. See you next time.